Word up, followers. Okay, here we go. We're getting into our new section on phase changes. I think this stuff is really exciting. It's really cool stuff that we're seeing an application of all of this higher order math and physics and how it's going to manifest into something physical and tangible, like what state is something in at a given temperature and pressure. Okay, so we start by recognizing that Gibbs is our important potential with respect to phase equilibria. And that's because Gibbs is, I'm going to make this slightly thinner, Gibbs is a function of temperature and pressure. Okay? And so if I expand on this, right, we remember we came up with the equation. Here, let me finish writing this and I'll describe it. So we know that the dg is the partial of g with respect to p at constant t times dp plus the partial of g with respect to now t at constant p dt. And we derived last time the fundamental equation of chemical thermodynamics. Okay, so that's fundamental equation of chemical thermo. Okay, and eventually when we go and expand on this beyond the canonical ensemble, where we're not really considering the number of moles, as we add on what happens to change the number of moles, that will give us an even better representation of the fundamental equation of chemical thermodynamics. So VdP minus SdT, and finally we realize the partial, and I'm going to switch to molar quantities, the partial molar Gibbs free energy with respect to the change in pressure at constant temperature is molar volume. Okay, so this derivative is V. And then similarly, the partial of molar Gibbs free energy with respect to temperature at constant pressure is negative molar entropy. So now what I have here to the right here is a free energy surface, okay, where we've got G on the z-axis, and then T and P represent the x and y axis. And then this would be a surface of a pure phase. So that means that could be the solid, the liquid, or the gas. Okay. And we can see here when we look at the relationship between G and T, so a graph of G versus T would give us a plot where the slope is negative entropy. And if we had a plot of G versus P, the slope would be positive volume, which is pretty cool. Okay. And so I'm also going to introduce a new idea here, chemical potential. And this was, I kind of briefly talked about this when I introduced the canonical, microcanonical, and grand canonical ensembles. So chemical potential is related to the grand canonical, okay? And so chemical potential gets the subscript mu, okay? And mu equals molar Gibbs free energy, okay? So it's just another name for the molar Gibbs free energy, okay? And note, it's not the change in Gibbs free energy, it's just the Gibbs free energy. So we could actually change this plot to be Gibbs or chemical potential, and that would work, all right? Okay, so moving along.